Hi, my name is Jonathan Norris. I'm a lead transportation and energy consultant with a firm called ICF based out of Los Angeles and a Voinovich School Master of Science in Environmental Studies alum. And I'm going to talk to you today about transportation decarbonization and transportation electrification. So we're going to cover a few different topics in today's presentation. First, we're going to start off with the role of transportation in climate change and with respect to greenhouse gas emissions. We're going to talk about what decarbonization means in the transportation space. And then we're going to talk about ways that decarbonization is happening through zero and near zero emission fuel and technology pathways. We'll talk about the emissions reduction potential of zero emission vehicles. We'll talk about the role of both federal and state policy in transportation decarbonization. And then we'll end with one example of innovation in the market, that is energy management and vehicle grid integration. And then we'll conclude and wrap up our main points. So let's start with transportation's role in climate change and greenhouse gas emissions. So if you're seeing this video, I'm assuming that you're already well-versed in climate change in a broader sense, and you understand the reasons behind why climate change is happening. You understand the greenhouse gas effect, and you understand what greenhouse gas emissions are. So with that background, if we look at transportation in terms of both global greenhouse gas emissions and greenhouse gas emissions in the United States, we can see that it is a leading factor in terms of overall greenhouse gas emissions in both of those levels. On the global side, if you look at the figure here on the left-hand side of your screen, you can see that transportation ranks fourth in terms of emissions by sector. It follows electricity and heat production, agriculture, forestry, and other land uses, and heavy industry in terms of greenhouse gas emissions. But in the United States, transportation accounts for the top contributor to greenhouse gas emissions by economic sector. Electric and power delivery is a close second, and then followed closely by heavy industry as well. So transportation emissions are a significant contributor both globally and especially here in the United States. There are many different types of emissions that come from vehicles and from transportation sources. You can see greenhouse gases down here on the bottom, but there are also air pollutants that are emitted from vehicles as well. And so air pollutants are typically solid or a mix of solid and gaseous emissions that either come out of a vehicle's tailpipe or come from other sources within and around the vehicle. So that'll include things like particulate matter. These are ultrafine particles that are emitted either through the engine of the vehicle or also through braking of the vehicle. So brake pads and rubber tires will meet to stop a vehicle. It causes friction, and then ultrafine particles of both of those materials will emit into the air, and these are smaller than the diameter of a human hair. So they're inhalable and are associated with adverse health impacts such as respiratory issues. There are also volatile organic compounds. What you see is the formula for benzene. So benzene is used in a number of polymers and plastics, which are used to form different parts of the interior of a vehicle. And so those will contribute to air pollutant emissions as well. And then nitrogen oxide, carbon monoxide, and sulfur dioxide are also air pollutants of concern. On the bottom, you see greenhouse gases. So carbon dioxide is the one that most people are aware of, but there are other greenhouse gases that are coming from transportation sources as well that are just as concerning. Methane, nitrous oxide, and hydrofluorocarbons are also greenhouse gas emissions that are associated with vehicle use and transportation more broadly. So those represented tailpipe emissions. There's also another category of emissions called life cycle emissions. And life cycle emissions includes tailpipe emissions, but also all of the other emissions that are associated with the production of fuel, the manufacture of vehicle and vehicle components, the operations and maintenance of vehicles, and other related activities such as mining to form the batteries and get the materials to form the batteries for electric vehicles. So you can see all of those different categories on the screen here. And so it's important when we're talking about emissions that they're often categorized in two forms, either tailpipe, what's coming out of the vehicle alone while it's operating, and then life cycle emissions. which is important for electric vehicles because it takes into account also the emissions associated with the production of electricity. Moving on here. So with that background, understanding how transportation fits in terms of climate change and emissions, let's move to talk about decarbonization. So decarbonization refers to the reduction of carbon dioxide emissions by using low or no carbon emission fuel and power sources. And importantly, while decarbonization has the term carbon within it, it also refers more broadly to the same efforts to reduce greenhouse gas emissions other than carbon dioxide as well. If you look at the figure on the right-hand side here, this is showing is transportation-related greenhouse gas emissions from transportation in terms of different vehicle types and sources. And you can see that in the United States, at least in 2019, passenger cars made up the vast majority of transportation-related greenhouse gas emissions, followed closely by medium and heavy-duty trucks, then by light-duty trucks, and then the other sources you see on the screen here. When moving toward efforts toward decarbonization, it's important to realize that there are 4 major things that need to happen before full decarbonization or significant decarbonization in the transportation sector. That includes the development and the deployment of zero and near zero emission vehicles. That includes the development and the deployment of zero and near zero emission fueling infrastructure to support and fuel those vehicles. It also includes developing and implementing supportive policies, regulations, incentives, and other programs. And finally, developing a market that incentivizes zero and near zero emission technology production and use. So as we go through the rest of this presentation, we're going to talk about all 4 of those items. And we're going to start with the development of zero and near zero emission vehicles. So the table on the screen is showing different types of zero emission technology pathways. The far column on the left is showing different categories of vehicles and other types of transportation. The next 2 columns are showing whether or not those types of transportation sources are applicable and for electric and hydrogen fuel, and then examples on the far right column. So the major takeaway with this table is that both electric powertrains and hydrogen powertrains are being developed for a number of different vehicle applications. So that includes on-road vehicles, light duty, medium duty, and heavy duty. That includes off-road equipment. That includes maritime vessels, rail, as well as aircraft. If we look at a few examples, if you look at the light duty on-road vehicle row, we're all familiar with electric sedans and SUVs. You might have seen that recently electric pickup trucks have started to come to market. And so those are being developed with an electric powertrain. There are also some light duty hydrogen fuel cell vehicles. The Toyota Mirai is probably the most well-known hydrogen fuel cell sedan and light duty vehicle. But these fuel sources are also being used for medium and heavy duty applications as well. So that ranges from everything from box trucks and delivery vehicles that UPS or FedEx or the Postal Service might use to deliver mail and packages to your door. It includes work trucks that utilities might use to repair broken or damaged power lines. It also will include step vans and shuttle buses being those types of buses that you might see at an airport to take you from the airport to a hotel. And so in this space, electric powertrains are being used more often than hydrogen powertrains, but hydrogen is being used for step vans and shuttle buses in the medium duty sector. In the heavy duty sector, we're seeing similar growth in both of those fuel sources. So that includes everything from transit buses to school buses, heavy trucks, and so on. And so on the hydrogen side, we see hydrogen transit buses. There's actually one in Ohio, or at least one, maybe a handful of them, that SARTA is operating. SARTA is the transit operator for the Canton and Akron area. And then hydrogen is also being explored for use in long haul, long range, heavy duty truck applications as well. On the electric side, all of those things are being electrified for heavy duty vehicles. And when comparing electric and hydrogen, hydrogen is being primed for mainly for use in long haul, long range, and heavy duty applications for a number of reasons, which we'll get into. Also, off-road equipment is being electrified. While we're not seeing hydrogen in this space, we are seeing the rollout of electric ground support equipment at airports. So this includes equipment to transport cargo around an airport, to put it onto airplanes, and so on. Electric forklifts are being developed, and then also electric yard tractors and other types of off-road equipment. Maritime vessels are also being electrified, and they also use hydrogen as well. So that is including tugboats and ferries and workboats, and so on. Many of you may already be familiar that rail is often developed with electric powertrains and electricity as a fuel source, but also hydrogen fuel cell powered trains are also being developed. And then in terms of aircraft, short haul electric aircraft is in research and development phases, not yet commercially available, but certainly being developed, and probably within the next few years, we'll see short haul electric aircraft that can take you, let's say, from Los Angeles to San Diego, or if you live on the Hawaiian Islands, you could hop from island to island. Hydrogen is also being used and considered in the aircraft space, but just like with on-road vehicles, it's being considered for more long-range applications. So all of these different vehicle types are seeing a growth in the use of both of those zero-emission sources as we seek to reduce carbon dioxide and broader greenhouse gas emissions from transportation. But zero-emission pathways are not the only pathways. There are a number of near zero-emission fuels that are in use and being developed as well. This includes renewable diesel, which is considered to be a drop-in fuel. So a drop-in fuel meaning that no modifications to the fuel tank, the fuel system, or any other components may be necessary before using it. Biodiesel, which is not necessarily considered a drop-in fuel, but is similar to renewable diesel. Gasoline can be made more renewable by using higher ethanol content, although there are some land use and habitat and biodiversity impacts that are associated if you look at a life cycle of higher ethanol content. And then renewable gasoline is not commercially available at this point in time, but similar to renewable diesel, it's something that's being developed in research and development stages to be a drop-in gasoline substitute. There's also renewable natural gas, which is often interchangeable in vehicles that use regular natural gas from non-renewable sources. And it's used pretty significantly in things like buses and trucks, especially heavy-duty buses and heavy-duty trucks. Dimethyl ether is a synthetic fuel carrier that's being developed currently in renewable and in research and development phases as well. And it's being explored as a carrier molecule for transporting hydrogen fuel, as well as a replacement fuel for heavy duty trucks. And then finally, sustainable aviation fuel is a biofuel that's used quite often by airlines, many airlines, to reduce the emissions of their air travel and fuel consumption. So both zero and near zero emission vehicle types and fuel types are being developed in this effort to reduce emissions and to reduce petroleum use in the transportation sector. Of course, as we mentioned earlier, the second item that needs to be developed and deployed in order to support decarbonization in transportation is fueling infrastructure. And so what you see on the screen here are four major types of electric vehicle charging infrastructure. The title of the slide is Electric Vehicle Supply Equipment, which is the technical term for an EV charger. According to the Alternative Fuels Data Center, which is an online and publicly available database and resource that is owned by the US Department of Energy, according to that resource, there are currently about 44,000 public electric vehicle charging stations that exist in the US today. However, given the rapid growth of electric vehicle registrations and general adoption in the US market, the International Council on Clean Transportation estimates that over 1 million public charging stations are going to be needed to support over 26 million electric vehicles by 2030. And so that represents over 1 million chargers that need to be developed, installed, deployed, and that's a significant infrastructure build out in the United States. It's also important to realize that as this infrastructure is being developed and deployed, there are different styles and designs of electric vehicle charging infrastructure, and they're set up to support different use cases or different styles or types of operation for different vehicles. By far, the most common type of electric vehicle charging infrastructure is plug-in charging. So you can see a picture of that on the top left, but there are also three other types. Wireless charging is being developed. You can see that in the picture on the top right. And I've seen that used for both light duty sedans, SUVs, and whatnot, as well as heavy duty buses. There are also overhead chargers. You can see that in the photo on the bottom left. So overhead chargers are typically very high power chargers that are used to support what is called opportunity charging. This is typically for transit buses that maybe have a long route. And if they're using an electric bus, the range of that electric bus may not be able to meet the full route's needs. And so a strategically placed overhead charger can deliver a very high power amount of electricity to fill the battery with what it needs in a relatively short amount of time. And then finally, on the bottom right is catenary infrastructure. This is most commonly found in use for rail systems. If you've ever been on a light rail, like the one in Cincinnati, you might have noticed that these overhead lines are charging the vehicle. And that is done through the use of a pantograph. The pantograph is the apparatus or device that you see on top of the vehicle that's making contact with those wires and keeping a steady charge of those vehicles. So while catenary is primarily used for rail systems, it is also being explored for things like heavy duty trucking. There has been a demonstration project in Southern California to examine the opportunity for using such systems for drayage trucks that operate by driving back and forth between seaports and warehouses and distribution centers to deliver goods between those two locations. So certainly not the most prevalent form of electric vehicle charging, but another form that's being explored and developed. So as with electric vehicle infrastructure, there are several different types of hydrogen fueling infrastructure. So hydrogen fueling can happen in retail stations that are very similar to gas or diesel fueling stations. The image on the top right of the screen is showing a retail hydrogen fueling center that's located in Southern California. But there are other forms of hydrogen generation and delivery as well. Most hydrogen that's produced in the United States is produced using natural gas as a feedstock. And it's typically done through a process called steam methane reforming. Steam methane reforming is the process of splitting methane molecules and capturing the hydrogen atoms and storing those hydrogen atoms and then converting it into a fuel source. There are other types of hydrogen generation that are less carbon intensive and emit less greenhouse gas emissions compared to steam methane reforming and the use of natural gas. One of those is electrolysis. You can see a picture of an electrolyzer on the bottom right of your screen. And so the way that this would work is by sending a high electric current through water to split water molecules, and then again, capturing the hydrogen atoms and then turning that into a fuel source. And so electrolysis is a lower emission form of hydrogen generation. However, one of the caveats is that it requires a significant amount of power to produce hydrogen in this way compared to other forms, other more conventional forms. And so while it might reduce emissions, it might be more costly to build and require more power to do so. And then finally, on the left, you'll see a picture of these hydrogen capsules, hydrogen fuel capsules that are being loaded onto an airplane. And so this is a concept that has been developed by a startup called Universal Hydrogen. While I'm not aware of any commercial applications for this yet, I haven't seen it in the market. It certainly is something that is in research and design and development phases. And this is a way to transport hydrogen fuel and load it onto hydrogen aircraft to support the operation of that aircraft. So just like electric vehicle charging infrastructure, a number of different styles and methods of delivering hydrogen to different types of transportation sources are being developed And again, that's necessary because different vehicles operate in different ways, and so they have different needs. So I want to talk a little bit about the barriers and challenges to zero emission vehicle infrastructure development that currently exist. So maybe the biggest one is the capital cost associated with developing this infrastructure. Capital cost being the cost of materials and labor and installation, as opposed to operating costs, which would be the cost of fuel and maintenance for a vehicle that's using it. The capital cost for both electric vehicle charging infrastructure and hydrogen fueling infrastructure is still relatively high, especially if the scale of the infrastructure you're developing is large and the power for, let's say, an electric vehicle charging infrastructure is large. Depending on, on a case-by-case basis, the infrastructure cost might be so high that it's actually prohibitive for some entities to develop it. There are lots of incentives that are being developed in the market still to this day, that programs are being developed to support entities that want to deploy this infrastructure financially because these costs are still high. However, the costs are expected to reduce over time as the technology matures. And that really goes to the second point here, which is the technology is new and in early stages of development. And so there might be hesitance among entities to adopt this infrastructure and deploy this infrastructure for two reasons. If the infrastructure and the technology is still in early stages of the technology curve, then an entity might be hesitant to adopt for future risk of obsolescence if the technology improves significantly in the future. And then secondly, because costs are expected to reduce over time, it may be more advantageous for an entity to deploy the infrastructure later when it's less expensive and the technology might be better. So that's currently a barrier to entry as well. As I mentioned earlier, deploying a high power or large scale infrastructure often is very costly. And one of the reasons that it's costly is because, especially with electric vehicle charging, high powered charging might require a utility to upgrade its own distribution grid equipment in order to generate and provide the electricity that's necessary to go through the charger and charge the vehicle. This can be very expensive. It can also be quite time consuming. Depending on how extensive your infrastructure build is, it can take multiple years to make all the upgrades to the utility infrastructure, to prepare a site for infrastructure development, and to ultimately deploy the infrastructure. And then next, charging an EV takes longer than fueling a gasoline vehicle. Fueling a gasoline vehicle takes a matter of minutes, but depending on how high powered your EV charger is, it's going to take maybe an hour or more to charge your vehicle. You can reduce the time to charge by increasing the power of your charger. However, increased power, as we mentioned, increases the cost of the charger and increase the likelihood that utility upgrades are necessary. And that really challenges the constraints that utilities have for delivering power based on the capacity of their existing grid infrastructure. And then finally, interoperability is a key concern for the electric vehicle charging infrastructure build out. Interoperability refers to the ability of EV drivers or hydrogen fuel cell drivers to use different types of fueling infrastructure, different providers of fueling infrastructure with ease and without any extra steps. Especially in the EV charging space, there are multiple charging providers, folks like ChargePoint, EVgo, Greenlots, and so on, and Tesla superchargers as well. And there are different styles of charging plugs. And so if your vehicle is not designed to match the charging plug that you're pulling up to and you don't have an adapter, you may not be able to use that charger. This is similar to the growing pains that the cell phone industry experienced whenever different network and carriers were coming out with cell phones and their own networks. Roaming was an issue in the early days of cell phones. And similarly, roaming is an issue for electric vehicle charging infrastructure as well. But there are entities working on all of these challenges, from nonprofits to universities and academic centers to consultants to manufacturers and so on. And so progress is being made. All right, so now that we've talked about zero emission and near zero emission technology and fueling infrastructure, let's move on to the emissions reduction potential of these vehicles. So what you're looking at on the screen here is the average well-to-wheel emissions for a light-duty vehicle, electric vehicle operating in Ohio, and then more generally, the well-to-wheel light-duty hydrogen emissions based on the way that hydrogen is produced. So focusing in on the figure that's on the left-hand side of the screen, this is from the Department of Energy's Alternative Fuels Data Center that we mentioned earlier. And it is showing the estimated average emissions for operating a light-duty vehicle, let's say, the car you use to get to school or work, and it takes into account the energy mix of Ohio's utility and energy infrastructure. So if you were to operate a fully electric vehicle, it would emit about half of the well-to-wheel greenhouse gas emissions than a gasoline vehicle in the state of Ohio. And then similarly, you can see the emissions numbers for plug-in hybrids and fully hybrid electric vehicles, like the Toyota Prius. If you move over to the figure on the right-hand side of the screen, you can see the similar information for, excuse me, for hydrogen fuel. And so on the bottom here, I want to explain the labels. So we have a benchmark of gasoline fuel. So this is showing the well-to-wheel emissions of gasoline fuel. And then we also have different forms of hydrogen generation. So as I mentioned earlier, steam methane reforming using natural gas is one of the most prevalent ways of producing hydrogen. So SMR stands for steam methane reforming. The G stands for gaseous fuel. So it's hydrogen delivered to the vehicle in the form of a gas. And then the L stands for liquid. So hydrogen delivered to the vehicle in the form of a liquid. And then solar refers to generating hydrogen using solar, a renewable energy source, and not natural gas, probably through electrolysis, like the electrolyzer that I showed in an earlier slide. And so you can see that while the emissions associated from activities from the well to get natural gas to the pump is lower than most other forms of hydrogen generation, the emissions associated with operating a gasoline vehicle is much higher. And ultimately, the overall emissions for gasoline fuel are much higher than these hydrogen emission estimates. And then also you can see that hydrogen generated from renewable sources, as you would expect, has a lower life cycle set of emissions than hydrogen generated from, let's say, natural gas and steam methane reforming. So more on this topic, what you're seeing here are energy economy ratios. So an energy economy ratio is a term that the California Air Resources Board developed to refer to the ratio of energy efficiency for one vehicle that's operating with a certain fuel type compared to a baseline, or what they're calling a displacement fuel type. So the way to read this is, if you look at the top row as an example, we're looking at electricity used in a light-duty battery electric vehicle or plug-in hybrid electric vehicle. The middle row or the middle column is showing that it has an EER value of 3.4, and the displacement fuel is gasoline. So what that means is that the California Air Resources Board estimates that electricity used in a light-duty, fully or plug-in hybrid electric vehicle, that vehicle can travel 3.4 times as farther on the same unit of energy as if it were a gasoline vehicle. And this is important for emissions because the higher the energy efficiency, the higher the energy economy ratio for a vehicle means that you use less fuel to get to the same range of travel. Therefore, limiting the amount of energy or fuel that you need to consume and limiting or reducing the emissions that are associated with burning or using that energy source. And so we looked at the top row, you can see similar values for hydrogen used in a light duty vehicle, and then both electricity and hydrogen used in heavy duty vehicles compared to diesel fuel. So we talked a little bit about the emissions reduction potential. We've talked about the types of technologies that are being developed to reduce emissions in transportation. Let's now move to the role of policy in transportation decarbonization. As I mentioned earlier, policy laws, regulations, incentives, and other related programs serve a really important purpose in transportation decarbonization. There are many different purposes of policies. Some of the main ones I'm showing here on the screen. So policies can be set up to either incentivize or disincentivize certain actions. That might be incentivizing the use of electric vehicles by providing a federal tax credit, which the United States does. Policies are also developed sometimes to establish a market or to support market development. I'm going to show an example of a market-based program that both California and Oregon have implemented to give you an example of that. Policies also sometimes are set up to mandate or require certain actions, or mandate and require that certain actions not be taken. Policies are sometimes set up to either clarify or establish a rule or some sort of decision and have a legal basis for doing so. This is often the case for Public Utility Commission decisions, for example. And then policies can also be established to establish study groups or working groups, and that can take place within a state with multiple agencies within one state, as well as interstate. And we're finding through research that interstate collaboration has served a really important role in aiding the development and deployment of electric vehicles and electric vehicle charging infrastructure, as well as other zero emission and near zero emission sources. So to give a few examples of transportation decarbonization related policies, let's look at the figure on the top left-hand side of the screen. What this is showing is the percent reduction in carbon intensity from transportation related fuels in California. So this is part of California's low carbon fuel standard. The low carbon fuel standard is a market-based program that incentivizes fuel producers to reduce the carbon intensity of their fuels. They can either take measures to reduce the carbon intensity of the fuels they produce, or they can purchase credits to make up for a lack of doing so. Those credits are then traded on a market. And so you have fuel producers on one side, and then you have fuel consumers on the other. This program is also really advantageous for anyone that's deploying electric vehicle charging infrastructure, such as, let's say, a retail shop center that wants to provide charging infrastructure for its patrons, or a commercial fleet or a transit bus fleet that deploys charging infrastructure to charge their vehicles and make sure they can operate every day. For the consumers that deploy charging infrastructure or use hydrogen fueling infrastructure or so on, they receive credits based on the amount of energy, clean energy that they're consuming and producing, or not producing, but consuming through their infrastructure and into their vehicles. And so they can ultimately earn those credits and then sell them on the market, which can be a really significant reduction in operating costs, a really significant source of revenue for those consumers. And so back to the figure, this is showing the current state of carbon intensity reduction in the state of California as a result of the low carbon fuel standard. You can see that they are well on track to meeting their goal of 20% carbon intensity reduction by 2030. Another type of policy that's been implemented, if you move down to the figure on the bottom left-hand side of the screen, another type of policy that's been implemented, or program rather, are utility make-ready programs. So make-ready programs are programs that are developed and deployed by electric utilities to support fleets in their service area in developing the infrastructure that's needed to charge electric vehicles at their site. If you look at the figure, you can see that on the far right-hand side of that figure, you have the EV charger and you have the electric vehicle. But it's important to realize that behind the EV charger, there is a host of other infrastructure that is either owned by the fleet or by the utility that supports the movement of electrons through the charger and to the vehicle. So this includes, as I said, items that are on site and owned by the fleet, like the electric panel, but it also includes infrastructure that may either be on site or off site and owned by the electric utility. So that would be the electric meter, transformers, and then the distribution network, the electric wires that you see everywhere you go. And depending on how extensive the electric vehicle charging infrastructure how powerful and how large scale that needs to be deployed at a particular site, the utility grid infrastructure may need to be upgraded in order to accommodate that extra electric demand. There's also site preparation work that needs to be done. Trenching, so drilling concrete and laying conduit and wire to connect all these different components together also needs to be done. And so utilities increasingly are developing these programs to help fund and support fleets in developing what they call this make-ready infrastructure. So that's a financial incentive, but also some form of technical assistance for fleets to encourage them to adopt these vehicles and the infrastructure. If we move to the bottom right, another form of policy, as we mentioned earlier, are mandates and requirements. So the state of California has implemented a mandate that 100% of light duty zero emission, or I'm sorry, 100% of light duty vehicle sales must be zero emission vehicles by 2035. Similarly, 100% of short haul or drayage trucks being trucks that move back and forth between ports and warehouses, also need to be 100% zero emission by 2035. And similarly for heavy duty long haul trucks and transit buses and other types of buses by 2045. So this would be more of a stick than a carrot, more of a requirement than an incentive, but just to give you an example of what that might look like. And then to give a local example, Ohio has a vehicle acquisition and fuel use type policy that it implemented in 2015. And so what this policy says is that where possible, all state agencies need to adopt vehicles that are capable of using alternative fuels, and they must use those alternative fuels where it is reasonable in cost to do so. And so that is a style of policy that's prevalent among many states that's requiring state agencies to adopt these vehicles and use them. So policy certainly has a big role to play when it comes to electric vehicle and hydrogen vehicle and other forms of near zero emission vehicle and infrastructure adoption. Policy really sets the rules of the game by which all of these different market actors can play and respond to incentives and to market signals developed through these policies. So one of the last things I want to provide is we've talked about all the drivers of transportation decarbonization. We've talked about the types of vehicles that are being developed. We talked about the types of infrastructure that are being developed, as well as the challenges to doing that. We talked about policy and emissions reduction. And now I want to turn to one more narrow example of innovation in the transportation, decarbonization, and electrification space. And that is energy management and vehicle grid integration. So energy management is a central challenge for fleets of vehicles. So think of a transit bus agency, think of folks like FedEx or UPS that have a fleet of delivery vehicles and other forms of fleets that either through state mandates or requirements or on their own accord are seeking to transition to a fully or partial electric vehicle fleet. Historically, fleets have always had to be cognizant of their fuel consumption, and they've always had to take measures to reduce their fuel consumption, to reduce emissions and petroleum use. Now that electric vehicles are becoming more prevalent and fleets are adopting them, they still have to be cognizant of their fuel use. In this case, it's called energy consumption instead of fuel consumption. But there's an added layer that they need to be aware of and be mindful of as they charge their vehicles, and that is power demand. So I want to back up and give a few definitions to help you understand what I mean by that. So electric vehicles are considered a distributed energy resource. A distributed energy resource is a relatively small scale unit of power generation that operates locally and is connected to the larger power grid at the distribution level. Examples of this include solar energy, wind energy, battery storage systems, and electric vehicles. So when an electric vehicle charges, the charger is rated in its maximum output power capacity. And its maximum output power capacity is measured in kilowatts. So kilowatts are, as I said, a measure of power, and power is the amount of energy transferred per unit of time. So that's important to know. The other important piece of this is to know is the energy side of things. So if kilowatts represent power, kilowatt hours represent energy. And energy is the capacity to do work. Electric vehicle batteries are also rated in their energy capacity. So if you go and you purchase an electric vehicle, instead of asking them how big the tank is for the gasoline tank, how much gasoline it can hold, you would ask them how much energy capacity does the battery have. And so this is important because these two figures are going to dictate how much electricity you need to send to your battery when you're charging, and how quickly you can send that electricity depending on how powerful the charger is. So now that we have those definitions, let's take an example of why energy management is so important. So consider a transit fleet that is based in California. And because it's based in California, and because California has this mandate of zero emission vehicles by 2040, 2045, that transit bus fleet has to transition to 100% zero emission vehicles by 2040. Let's assume that they're doing that with fully electric fleets, all electric vehicles. And let's assume that the fleet has 350 buses. So they need to convert 350 buses to whatever their current fuel source is to electric buses by 2040. A typical battery capacity for an electric bus is around 300 to 325 kilowatt hours. So let's assume that as the battery capacity. Typically, transit buses can charge overnight because they're not operating at night. And so let's assume that the bus is connected to a charger for 8 hours every single night. Let's also assume that all the buses are charging concurrently. That means they're all charging at the exact same time for the same duration of time. This isn't advisable, and it's not what would actually happen in most situations. But for the sake of this example, let's assume that. And then let's assume that the buses are returning to the facility and hooking up to the charger with about 35% of their battery left. Typically, electric vehicles aren't going to go all the way down to 0% battery capacity before they need recharged. And so let's just assume that it pulls in at 35% and therefore needs 210 kilowatt hours per bus that needs to be delivered in that 8 hours. To do that, you need a charger that is about 26 kilowatts. And so every single charging plug for every single one of those 350 buses will need to deliver 26 kilowatts of power. That represents a peak power demand of 9.2 megawatts. And as a point of reference, the peak power demand of the Empire State Building is 9.5 megawatts. So we're talking about a lot of power. And again, this isn't how fleets would necessarily do this. And one of the ways they can get around this is through managed charging, energy management. So why is this a problem for the fleet? Well, in addition to the chargers being much more expensive, the higher power that they are, the operating cost for the fleet is likely to be exorbitantly high in this situation. And that is because utilities charge what is called demand charges. So demand charges are monthly dollar per kilowatt charges that are levied to offset the cost of delivering a consistent level of electricity. They're typically determined by collecting information from the electric meter and then using the highest power demand in any given 15-minute interval each month. And historically, these demand charges were used by utilities to incentivize big commercial and industrial facilities to reduce their power demand. The thought was that if you charge these higher demand charges, manufacturing facilities, steel making facilities, malls and large retail centers, big consumers of electricity would respond by finding ways to increase their energy efficiency and reducing their power demand because it's a disincentive to have to pay those demand charges. However, EV charging wasn't thought of whenever these demand charges were developed. It wasn't necessarily a market that had been developed. And so currently demand charges represent quite a conundrum for fleets. It can make it really, really expensive for fleets to operate a full fleet of electric vehicles. And so one way to get around this is by the introduction of smart charging and energy management systems. So on the left here, we're showing just a simplified diagram of what smart charging can do to the power demand of a fleet that's charging. So if you follow that pink line and you see the curve, and that represents the power demand across time for a fleet. Smart charging works by leveling out that power demand over a larger amount of time. So the way that smart charging works is that you have electric vehicles, electric vehicle charging infrastructure, and then operators that use software and data to actively manage the charging activity across a full fleet of vehicles. You need, of course, you need the EVs. You need the EV chargers that are able and equipped with smart charging capabilities. And what that means is that the chargers can talk to each other, and they can also throttle the amount of power that they're delivering to the vehicle at any given time. You need software systems, data systems, and communication systems, all to integrate the chargers, integrate the software, and so that all of the different entities in this system can communicate with each other effectively. And ultimately, what you're seeking to do is to reduce the peak power demand. And so you're only charging what you need, and you can do it in a more scheduled, efficient manner. So that's smart charging. Smart charging is one type of vehicle grid integration. So if we move to the figure on the right, this is a diagram that's showing a simplified setup of vehicle grid integration. Vehicle grid integration can be thought of as an umbrella term that refers to all the different ways that electric vehicles can communicate with, share information, and share electricity with the grid, as well as other facilities like local buildings and other loads. So smart charging is one part of vehicle grid integration, but one of the other main parts of vehicle grid integration is called vehicle to grid. And that is characterized by a bidirectional flow of electricity. So instead of the electric vehicle just sending electricity, or I'm sorry, the electric vehicle charger just sending electricity to the electric vehicle, now in a V2G enabled system, the electric vehicle can send electricity through the charger and either to the grid, or if it's a vehicle to building system, it can serve as a source of backup power and send electricity to the building, and can really be used as a distributed energy resource, like solar panels, like battery storage. It can be a source of backup power, and it can also open up a form of revenue generation for fleets and vehicles that operate with this capability. So let's stay on the right-hand side of the screen here. If we're looking at the benefits of vehicle grid integration for fleets, as I mentioned, this can open up a source of revenue. So if you are participating in a utility-led electric market where you are either providing demand response, which means you are responding to signals from the utility to either throttle your power up or down, you can get paid for that. If you are sending electricity to the utility to help them balance the frequency and the generation and demand on the grid, you can also get paid for that. And then, as I mentioned, you can also provide EVs as a source of backup power for buildings, facilities, and other loads. And then the use of vehicle grid integration can also reduce the need for the amount of charging infrastructure that you need. The same goes with smart charging. If you have the ability to optimize your charging activity, then you can right-size the amount of infrastructure that you need to deploy and therefore reduce upfront capital costs. If we move back over to the left, the benefits of smart charging are similar. For fleets, you can get reduced energy costs, you can reduce your demand charge costs, you can yield cost savings from using your energy more efficiently, and so on. And then for utilities, both of these types of innovative energy management systems can provide more stable and predictable demand from the fleets the electric utilities are servicing. And it opens up an opportunity to work with these fleets to help support the grid and its operations. And finally, when it comes to energy management systems and vehicle grid integration, one of the other main benefits is grid resilience. So if you have a more distributed network of electric vehicles that can be aggregated and used to provide backup support to the grid and to other facilities, then by nature, your grid is a bit more resilient. So to be resilient, a grid must have the capability to anticipate, absorb, adapt to, and rapidly recover from disrupting events. This can be things like a hurricane that knocks out some of the distribution grid. This can be things like just critical peak power events. If everyone is coming home and turning on all their appliances, then the demand of the whole community is going to go up. And so by having these assets, these electric vehicles as supportive assets, you can reduce peak power demand for the whole grid. You can enhance grid resilience by having these vehicles be an integrated source of mobile energy storage, and provide sources of backup power for a number of different entities. So summarizing what we've covered today, we've talked about transportation decarbonization and what it means. We've talked about the role of transportation in climate change and how much transportation contributes to greenhouse gas emissions. We've talked about different ways and technologies and pathways that the market is developing to reduce emissions in the transportation sector. We talked about emissions reduction potential. We also talked about policy and its role in transportation decarbonization. And then finally, this example of innovation in the industry of energy management systems and vehicle grid integration. And so I hope what I covered was informative. If you have any other questions about transportation decarbonization or transportation electrification, my contact information is on the screen. There is so much more beneath this. This was really a high-level summary. And so if you're interested in this, please feel free to send me an email and get in touch. Thank you.